All right, good afternoon, guys. We'll get started. So before we get into the content of what we're going to do today, I'm going to do some housekeeping stuff. This is a reminder about assignment 2, which is due tomorrow by 4 p.m. in the drop boxes. The assignment solutions are ready to go for you guys to help, to assist with you guys studying. I'm going to post the assignment solutions exactly as soon as I finish collecting the assignments tomorrow, so you guys have the most amount of time to study with them. What that means is I'm not going to take any late assignments. Right? I don't think I've been ambiguous about this policy, but I still tend to get emails after the assignment deadline is passed. No late assignments. I'm going to post solutions right away. I can't accept late assignments as a result of that. Do keep in mind that this assignment is due at 4 p.m., not 5 p.m. like last time because of the change of the lab's hours. But I told you that at the beginning of the assignment 2, which means you've known it the whole time. So that's not going to be a valid excuse. Test 2. So I sent out an email about this a few hours ago. Test 2 is going to be the week we get back from the break. So next week is winter break, so we won't have class or office hours or tutorials or anything. Test 2 will be as soon as you get back. So unfortunately for some of you, that means Monday morning at 8:30 after the break is over. That is unfortunate, but I don't schedule the tutorials. Be ready for that. Technically, Test 2 covers until the end of tonight, although I've already made up Test 2, and I'm not going to lie to you for no reason. Test 2 really only covers up until the end of last lecture. So nothing I say tonight will be on Test 2. That being said, it'll be on Test 3, so don't just go to sleep. And also, some of the stuff I do tonight you might find helpful. So for example, if I do a summation tonight, you might find that helpful for your test next week, even though I officially covered summations last class. So you still might find it helpful, but all of the types of material you need covers until the end of last class, which is lecture 11. I've already posted a sample test 2 on CU Learn. Remember what happened last time. The sample test was exactly like the real test. That exact same thing is going to happen this time. Do the sample test. If you are unable to do it, talk to me, talk to the TAs. Okay, we don't have office hours officially next week, but I'll still be around. If you send me an email, I can help you. And if you'd like to meet with me, we can try to work something out. Okay, so the TAs, you won't be able to as much. They don't have office hours next week. I'm an instructor. I'm here full time, so I can be a little bit more flexible and helpful for you. So let me know if you can't do the sample test. If you're mystified by something, you're going to have trouble on test 2, I promise. All right, any questions about assignment 2 or test 2? Everyone sees what's coming? All right, so what we're going to talk about today is algorithms. This is the next topic in this course. Comp 1805 is not a course on algorithms. You have to wait a little bit for that. That's Comp 3804 and in some sense Comp 2402. That being said, as computer scientists, this is our bread and butter. So it's important to introduce the idea now. I'm going to introduce the idea in the context of analysis, which will lead nicely into the next topic of the course. So this is a brief detour to sort of set us up for what we're going to do for the rest of the course. All right. What is an algorithm? Does anyone know? Yeah?
Is it a method for repeatedly solving the same problem?
Well, what do you mean by same problem?
I don't know what I said.
Like the same type of problem? So for example, if I asked you to sort a list, yes. Your algorithm wouldn't just apply to the same list over and over again. It would apply to any list. Yeah, exactly. So that's what it is. An algorithm is a method of solving a particular type of problem. All right. So I'm going to take that definition and I'm going to add 2 things that I think are important to it that you think probably goes without saying, and maybe you're right. An algorithm is a finite sequence of precise instructions for solving a problem. So this is basically what you said, except I've been a little bit careful and added these two keywords here. One of them is finite, and one of them is precise. And then the last important thing is solving a problem. So these are the three key things that I think make an algorithm. So it has to be finite. You can't say the solution of your problem is to check every integer and see if that's the answer. That's not okay. It has to be precise. Precise means precise enough for a computer to do it. Right? When you sit down and write a computer program, that's very precise because the computer does exactly what you say. And the last thing is that it has to solve a particular predefined problem. Questions?
Is sequence in the same way that we've been talking about like mathematical sequences, or is it?
I mean in the sense of an ordered list. Yeah. Yeah?
Oh, just talking about finite. Can an algorithm take limits?
What do you mean, can it take limits? Can it compute a limit?
Yeah, can it use limits?
So that becomes somewhat difficult. So one thing it might be able to do is use some kind of computer algebra system to come up with symbolic representation for what the limit is. That's okay, we know how to do that. It's tricky, it's well beyond the scope of this course. The other thing you might say is, okay, well, can it numerically approximate a limit? And that's another thing that we can do. So you come to within some value, and you have some bound on how far away that your answer can be. Those would both be considered algorithms.
All right.
Other questions? All right. So you can kind of think of an algorithm like a recipe for solving a problem, right? A recipe has to have very precise instructions, right? It's not like take 2 cups of flour plus or minus 1 cup. That's probably not going to work out for you. And it has to be finite, right? If you're looking forward to having some cake and the recipe is infinitely long, that's probably not going to be that delicious. All right. So let's see an example of an algorithm. So here is an algorithm for outputting the largest number from a list of numbers. Okay. And does anyone know how this might go? Probably seen something like this in a programming class. How do we do this? Yeah?
Well, I was going to say check the whole list, but then if it's infinite, that wouldn't work.
So the list is finite. I don't give you infinite input. That's cheating.
Then check each element, and if it's bigger than the previous, make it the biggest one.
Yeah, so what you're basically saying is have some temporary variable that is the biggest thing you've seen so far, and scan through the list, and anytime you see something bigger, put that in there. Right? All right. So that's the standard thing. So here are the steps of how you would write that out in English. So set a temporary variable to be the first number. All right, so now you compare the next number to the temporary variable. And one of two things can happen. The interesting thing is if it is larger, set the temporary variable to this number. And then step 3, well, you just repeat step 2 until there are no numbers left. And I would argue that this, well, so step 4 would be output the number, I guess. Step 4, output the value of the temporary variable. that would count as an algorithm. It has a finite number of steps. So there's 4 steps here, but in fact step 2 gets repeated for as many numbers as there are in the list. But because the list is finite, this number will also be finite. And it's precise because, well, by reading this, you know exactly what's going on, hopefully. The other reason that you probably think this is going to be precise is because if you wanted to sit down at a computer and program this thing, you could probably do that without much work. Somehow all the work's been done for you. This is the technique you use to solve it. Everything else is just kind of a matter of syntax. That's not very much work. And it solves the problem. So this thing really will output the largest number. If I made a mistake somewhere in writing this up, and maybe it doesn't output the largest, it outputs the smallest for some reason, well then this wouldn't be an algorithm because it doesn't solve the problem I said it would solve. It might be an algorithm for some other problem, but it wouldn't be an algorithm for this problem. This is the one we're interested in. So any questions about how this algorithm works? All right, so let's look at another algorithm. Here's an algorithm for outputting the index of the number x in an array of n numbers. So you have an array in your favorite programming language, Python, and you want to find the number x, and the answer you want to give to that is the index that x is at. So if x is the 3rd thing in the array, you would return 2. Yeah, 2. Okay, you're thinking like computer scientists. All right, so the way you do this is you just look at every element, and if it's the element you wanted, then you return whatever that index is. So step 1, look at the first element. If it is x, return 0. Step 2 says look at the next element. If it is x, return that index. It's a little vague. I'll get back to that in a second. Step 3 is repeat step 2 until the end of the array is reached. And at that point, if you reach the end of the array, what's the answer? Yeah, it's not there. So the nice thing about explaining algorithms in English is you don't need to worry about any particular programming language, right? In Java, you might return null. In Python, you might return none. In Perl, you might return undef. We don't need to worry about this, so we can just say return not found. And that just means whatever the right thing is in the language you're working with. The details don't matter. So is this an algorithm? I mean, probably, right? It doesn't spell everything out in complete detail. There is this part here that says that index. That's a little ambiguous. That tells you would probably need some other counter to keep track of which index you're currently examining. So this is kind of a gray area. It's pretty precise. It's clear what the idea is. But you do need to do a little bit more work to go from this sort of English description of what's going on to actual code, if that's how you want to think of it. I would still consider this an algorithm. I would just consider it a little less precise. Yep?
Are all algorithms, the first one is also recursive? Either one is recursive algorithms?
You don't need to view this as recursive. It's not, you could easily interpret the first one as iterative. That would be fine. You can certainly implement it recursively, and that's okay too. But no, there's no requirement to think either way. This is just a description of what's going on. The implementation of how that happens is a separate issue. Other questions? All right, so these are kind of simple algorithms. They're not that interesting, although they do get used all the time. What's a bit more interesting is the problem of sorting. So sorting is a problem you'll encounter all the time in your career as a computer scientist. For the sorting problem, you're given a list of elements that can be ordered. So usually we think numbers, but it could be anything that has an order to it. And we'd like to rearrange it so that the elements are in non-decreasing order. Non-decreasing order. And I don't say increasing order because maybe some of them are the same. And in that case, well, if you have 5 and 5, that's not increasing, but it is non-decreasing. So that's the sorting problem. For the sorting problem, we're given a list of elements that can be ordered. And for our examples, it'll be numbers. But you could also order strings, for example. You could sort them alphabetically. That would be an ordering. And what you'd like to do is rearrange the list so that the elements are in non-decreasing order. So as an example, let's say I gave you 3, 2, 5, 1, 4. I'd like you to change that to be 1, 2, 3, 4, 5. This is non-decreasing order. And in fact, if I had a second 5 in here, I could stick that at the end too. So that's what non-decreasing order is. Is it clear what the problem is? This isn't a crazy problem. It's just sorting. It's something we all do all the time. It's what I didn't do when I returned your first assignment. Okay, so what we'd like is some way of solving this problem. So what that means for us is we'd like some algorithm that solves the problem. One algorithm that does this is called bubble sort, and that's the first algorithm we're going to look at that's sort of somewhat complicated. So you might have encountered bubble sort before, maybe in Python or Java or whatever. We're going to look at it from a theoretical standpoint. So I'm going to give it to you in what's called pseudocode. That's code that is not in any particular language, but is hopefully easy to translate into most languages. So there's sort of some similarity in syntax, but we don't worry about the details so much. It's what is the algorithm trying to say? All right, so the way bubble sort works is by looking at pairs of elements and checking to see if they're out of order. So that means we have a big thing before a little thing. And if they are, then swap them so that they become in order. And if you do this enough, then eventually the list has to be in sorted order. Because the only way the list is in sorted order is if there are no pairs that have that property. So bubble sort works by examining pairs of elements and swapping them if they are out of order. And the idea is that elements that are very big bubble up the list until they get to the end. Or you could think of it the other way, elements that are very small bubble up to the front of the list where they should be. This is the idea. So all you need to do is make sure you do this enough times. That's really the critical thing. So the pseudocode looks like this. The way I'm going to write pseudocode in this course is I'm going to say the name of the algorithm. so bubble sort. And then a list of parameters, so for us that's the list. Let's say the list is A1, A2, A3, all the way up to AN. So these aren't in sorted order. These are just in whatever order they're given to me. And now I'm going to write the code. So this looks a lot like a function definition if you're coming from, say, Python, except there's no def in front of it. The code looks like this. I have a for loop. For I gets 1 to n minus 1 do. So this is a for loop that runs from 1 to n minus 1. I use an arrow here instead of equals because a lot of these algorithms are kind of mathy, and I might want to use an equal sign somewhere. And in math, we know exactly what an equal sign means. In programming, equal signs don't really mean equal signs as we know it in math. So that's why I'm using a separate symbol here. I don't like to reuse symbols when I can avoid it. So we have a for loop that goes goes from 1 to n minus 1. Inside that for loop, I'm going to have another for loop, and that takes j from 1 to n minus I. And now I'm going to look at the pair aj plus 1. So if aj is bigger than aj plus 1, so aj is before aj plus 1, but it's bigger, well then I have to swap them. So I swap aj and aj plus 1. And this is the entire algorithm. This is what bubble sort is. It kind of feels a little Python-y. That's because pseudocode is designed, or Python is designed to look like pseudocode. This is how I will usually write it. And we'll see more examples as we go of other sort of constructs that you end up with. Other than the fact that maybe it's not clear why this works, does anyone have any questions about it? In what sense? I mean, they both sort it, and they both take about the same amount of time to sort it, as we'll see. I mean, I'll do insertion sort in a few minutes, and we can talk about the differences then. Yeah?
So we're going to talk about big O notation?
Yeah, in fact, that's basically why we're talking about algorithms, so that we can lead into big O notation. Yeah?
Is there usually some sort of flag to tell us if there were any swaps made, so X immediately says work?
Yes, so there are definitely ways to improve this algorithm. This will do some needless work under certain conditions, and we will indeed talk about that. Other questions? All right. So let's do an example to see how this thing runs. Because the best way to understand an algorithm is to try running it yourself. So I'm going to do an example. I'm going to have the array 3, 2, 4, 1, 5, which is a fun array to sort. All right, so notice that if we want to sort of run through this algorithm, really what we're doing is simulating it ourselves. So we're going to have to keep track of these variables. So I goes from 1 to n minus 1. So notice that in this case, n equals 5, because there's 5 elements. And for now, we're going to assume that the indexing starts at 1. So these elements are A1 through A5. And that's implied by the fact that these parameters are labeled that way. I don't love that, but usually when we describe algorithms in pseudocode, we use 1-based indexing, unlike in programming where we used 0-based indexing. Wasn't my choice. All right, so now we need to look at the different variables we have. We need to keep track of I and j. Those are my two different variables. We also have all the parameters, but we can deal with them later. So I have this outer for loop that goes from 1 to n minus 1. So that means I goes from 1 to 4. So let's have columns for that. I equals 1, I equals 2, I equals 3, and I equals 4. So this is the first part. And now let's start running through it. So it starts at I equals 1. That's the very first thing I start at. And initially, j equals 1. So this is the first iteration of the first iteration. The first inner iteration of the first outer iteration. All right, so what do we do? Well, let's make our array. So we have 3, 2, 4, 1, 5. That's initially our array. And AJ is A1, which is this right here. And AJ plus 1 is A2, which is this right here. And we ask ourselves, is AJ bigger than A1? So is AJ bigger than AJ plus 1? So is 3 bigger than 2? The answer is yes. So that means we have to swap these. All right. So that means we now have 2, 3, 4, 1, 5. And this is how we enter j equals 2. So when j equals 2, we have the result of j equals 1, which is 2, 3, 4, 1, 5. So now we look at AJ, which is 3, and AJ plus 1, which is 4, right? Because it's A2 and A3. And we ask ourselves, is 3 bigger than 4? No. So we're happy. Nothing has to be done. So this is, I'll put a little check mark here to mean it's okay. Now we look at j equals 3. We have 2, 3, 4, 1, 5. And we're looking at A3 and A4. So is 4 bigger than 1? Yes. So we have to swap them. So now we go to j equals 4. And we have 2, 3, 1, 4, 5. And we look at A4 and A5. Is 4 bigger than 5? No, so we're okay. And now we think to ourselves, do I keep going? Do I go to j equals 5? Well, j goes from 1 to n minus I. I is 1, so j goes to 4. So we're done. Well, we're done the case when I equals 1 anyway. Does everyone see how this worked? This is okay? So now we go on to I equals 2. We start off with what we left off with before. So 2, 3, 1, 4, 5. This is the j equals 1 case. All right. So in the j equals 1 case, we look at A1 and A2. Are they in the correct order? Yes. So we're happy. 2, 3, 1, 4, 5. Now we're looking at 3 and 1. Are they in the correct order? No. So we swap them. So we have 2, 1, 3, 4, 5. And now we look at 3 and 4. Are 3 and 4 in the correct order? Yes. And remember, j goes from 1 to n minus 1. N is 5, I is 2, so it goes until 3. So in fact, we don't do j equals 4 when I equals 2. We skip that. We don't need to do that anymore. And we'll see why in a second. All right, so now I go on to I equals 3. It starts with 2, 1, 3, 4, 5. And we examine 2 and 1. They're out of order, so we swap them to get 1, 2, 3, 4, 5. And in fact, we're done now. We know we're done, but the algorithm doesn't know it's done. So it now checks this next one, 2 and 3, and they're in the correct order. Remember, this inner for loop only goes to 5 minus 3, which is 2. So in fact, I don't go to j equals 3, and I don't go to j equals 4. And then the very last one is I equals 4, in which it checks 1 and 2. And those are already in the correct order. I don't need to do anything past that, so I can ignore those. And notice that the list that we end up with is 1, 2, 3, 4, 5, and it is, in fact, in sorted order. Was everyone able to follow sort of what I was doing? Just simulating what happens when we run the algorithm. All right, so why don't we have to do j equals 4 when I equals 2? Why can we skip that? Yeah?
Well, we already know that the very last two elements are already in order. This is bubble sort. All we can concern is that after the first run through, the highest value will be in the farthest right area.
Right, after the first iteration, 5 is where it should be. Right? It has to be. It's the biggest thing, so it would have got swapped in every single comparison. So after the first I iteration, the first outer iteration, the biggest thing is exactly where it should be. So there's no point in doing a comparison between this thing and that thing. There's no point because this over here is already the biggest. So we don't make that comparison because we already know the outcome. After that iteration, 4 and 5 are exactly where they should be. Because it's the same effect as sorting a list that is one element shorter. Does that make sense? Okay, so on the very last iteration, 3, 4, and 5 are all where they should be. So I don't need to compare them to anything. And I just need to sort 1 and 2. And I can do that by swapping it or not. So in this case, I don't have to. So all of this stuff here is sorted. In this case, it's just one thing that's sorted. That's easy. In this case, it's 2 things that's sorted. And in this case, it's 3 things that are sorted. So I don't need to worry about those cases. They're done for me. And that's why I can not execute all of those extra iterations of the inner for loop. Now you might notice that in fact this list got sorted when I equals 3, but nothing told the algorithm that. One thing you can do to bubble sort to make it go a little bit faster under certain conditions is to check to see if it did any swaps in one of the outer iterations. And if it doesn't do any swaps in an entire outer for loop, well then it's done. You don't need to continue to the next one. In this particular case, we only saw that very close to the end anyway, so the savings aren't huge. All right, so that brings up a natural question. Which is, how long does this take? So how long does this algorithm take to run? Yep. So in fact it's O of n squared, but we'll come to the big O notation later. I mean in general. So if you were talking to your boss at a software company and they asked you, how long is this code going to take to run? They're probably expecting a number, right? Like it'll take 30 seconds or something like that. Yeah? Okay, so this is a little bit better because now it's somehow more precise. What you're saying is it depends on how long the list is, for sure, right? It's going to take longer to sort a list of 1,000,000 elements than it will to sort a list of 10 elements. No one's debating that. So that's good. The answer is it depends on the number of elements, for sure. Okay, so let's say you sat down at home and coded this thing up in your favorite programming language, and I said, okay, here's a list of 1,000 elements. How long is this program going to take to run on it? What would your answer be then? I mean, can you give me an answer? Yeah? Yeah, so it still depends. It still depends. So you know the exact number of elements in the list, but that's still not enough to answer the question. It depends on the processor speed. It depends on the operating system. It depends on the hardware. So, for example, the amount of memory you have. Maybe the list is so big that it can't fit in RAM. Maybe it has to go to your hard drive. That will make it take a lot slower. It will depend on the implementation language. Right? Maybe if you code it in Java, it will go very slowly, but if you code it in C, it'll go very quickly. That's not really the case anymore, despite what some prima donna programmers might tell you. So implementation language, all sorts of things. It really depends. There's no one single answer to this question. If you wanted an answer, you would run your program 1,000 times and then take the average, and that would be like an answer. Yeah?
So I know it depends on the initial state of the elements, right? Because a list of 1,000 elements where only 2 are out of order will sort much faster than a list of 1,000 elements where all of them are out of order.
So in this particular case, as we've written bubble sort here, it will take the same amount of time regardless of the order. But if we do make this optimization where if we go through the outer for loop and nothing swaps, then we're done, then yes, if it's initially sorted, we won't have to do a lot of extra work, for sure. So in fact, not just the size of the list, but also the structure of the list will have a strong effect on how long this kind of thing takes. Other thoughts on this? All right, so it's not a simple matter of saying, oh, it takes 30 seconds. Right? It's much more complicated than that. Even if you knew the exact elements, it's not easy to predict how long it will take in seconds because every computer is different and that's just the way it is. So we will come up with ways of answering this questions. A few of you have alluded to it, whether it's big O notation or precise expressions for how long these things take in terms of the size of the list or something like that. Before we do that, though, I'd like to talk about another algorithm, and that's insertion sort. So insertion sort is another way of sorting an array, but it works a little bit differently. So it works by scanning the array left to right and looking for an element that's in the wrong place. So it's out of order somehow. When it finds such an element, it finds where the element should be and then puts it there. But of course, if you're going to put an element in the middle of an array, you have to make room for it. So it looks for where it should go, bumps everything else down one, and now there's a spot for it. That's what insertion sort does. So it works by scanning the array left to right, looking for an element that's out of order. And when such an element is found, it looks for where the element should go. So I should say when or if such an element is found, it looks for where the element should go and places it there. But of course, it can't just stick it in there. It has to make room for it. So it pushes back elements between where it was and where it should be. So if that's a bit difficult to understand, you might have a better time if we did a little diagram. So after it does this, the scan continues, I should say. So the idea is this. We have some big array here. And we start going through this array until we get to an element that's out of order. So all of these elements are in increasing order, or non-decreasing. But then this element here, it's somehow not where it should be. So it's smaller than those elements. These elements are bigger. All right. So if that happens, what I now know is this element here is small, so it should go earlier in the array. Okay. So what I do, I'm just going to make this a little bit bigger for me. What I do then is look back in the array to see where does this thing actually belong. And maybe the first place that I see that it should go is here. Because the thing over here is smaller than it, and the thing over here is bigger than it. So the place this element should go is over here. But I can't just stick it there, because there's already an element there. So I need to make room for it. So I take the element that was there and put it there. But again, I can't do that because there's already an element there. So I have to take that element and shift it down. So I take that element, shift it, that element, shift it, shift it, shift it, and so on. And this keeps going until I get here. And then I say, oh, there actually is room for that element there because I took out the element that was there that was out of order. So this is all insertion sort is. It just takes an element and puts it where it should be. This is how a lot of people, if you've ever played poker or another card game and you want to sort your hand, this is probably what you did, except in that case, you don't need to make room for a card. You just slide it into that spot, right? In an array, you need to make room for it by shifting everything down. All right, so let's look at the pseudocode for this thing. Any questions about the sort of high-level description before I do the pseudocode? Because if the description doesn't make sense, the pseudocode definitely won't make sense. All right. So, insertion sort also takes a list of elements. So let's say A1, A2, A3, all the way up to AN. And the way it works is this. We have a for loop, just like we did before. So for, and I'm going to use j gets 2 to n, which is kind of weird. I'm starting it at 2 instead of 1. The reason is the first element is already kind of in the right place if I just look at the elements so far. All right. So now I set a few temporary variables here. K I'm going to use to denote aj. And I is initially j minus 1. And now I say, while I is bigger than 0 and AI is bigger than K, I do the following thing. I shift everything down. So essentially what I'm doing here is making room for something if I need to make room for something. And the way I do that is I set AI plus 1 to be AI, and that shifts AI down 1, and I to be I minus 1. And then the very last thing I do after that while loop is I set I plus 1 to be K. So K here is the element that I'm worried is maybe out of order. And what the while loop does is it looks back until it finds the place it should be. Now it is possible that it's already where it should be, and in that case AI is bigger than K, well that'll be false. So I'll be okay, I won't do anything. All right. I would consider this pseudocode to be hard to understand because it's not at all obvious how this matches up with the description of the algorithm. So this is why I like English descriptions of algorithms, because when you describe the algorithm in English, it's very clear what's happening, right? I'm putting something where it should go, but to do that I have to bump everything down. This is more precise, but the penalty you pay for that is that it's harder for us to understand. It's much easier for the computer to understand, harder for us to understand. So what I'll do is I'll run through an example of how this works, and hopefully that will convince you that this algorithm makes sense. So, let's say I want to sort my favorite array 3, 2, 4, 1, 5. This is what I would like to do. All right, so initially I have the array 3, 2, 4, 1, 5. And j, so I'll do this in a different color. The indices I'll put in blue. So this is index 1, 2, 3, 4, and 5. Initially, j is 2. And remember, j is an index. It just so happens that 2 is at this index. K is going to be aj. So k is 2. And I is j minus 1. So 2 minus 1 is 1. And now I say, okay, well, I've set up k and I, so now I do my while loop. So while I is bigger than 0, I is 1, and 1 is bigger than 0, and ai is bigger than k, so ai is 3, k is 2, 3 is in fact bigger than 2, so I'm going to go into this while loop, and I'm going to set ai plus 1 to be ai. So that means ai plus 1, which is 2, becomes ai, which is 3. So now my array looks like this. And right now it's kind of in an inconsistent state because there's 2 3s but no 2. All right. And I set I to be I minus 1. So now I is 0. All right. Okay, so now I go to the top of my while loop again, and it says, while I is bigger than 0, but I equals 0. So I know I'm finished my while loop. So I go to the line of code after my while loop, and that is ai plus 1 gets k. So I is 0, which means I plus 1 is 1, and k is 2. So ai gets 2. And now notice that I've sort of restored my array in some sense. So what this had the effect of doing was swapping 3 and 2. That's really what this did. Does everyone see how I did that? All right. So this is the first iteration. So now we go to the second iteration. Now we have 2, 3, 4, 1, 5. Okay, so now j is 3. And k is just aj, so k is 4. Okay. And I is j minus 1, so I is 2. Right? Because j is the index, remember. Does that make sense? Okay, so now that I've set it up, I go through my while loop, and the while loop says, while I is bigger than 0, well, 2 is bigger than 0, and ai is bigger than k. Okay, ai is 3, k is 4, so that says 3 is bigger than 4. That's false. So that means I skip my while loop entirely. I don't do anything in it. And I just move to the next line, and that says ai plus 1 gets k. Well, ai plus 1 is 4, and k is 4. So 4 gets 4. That has no effect, right? So I don't do anything. Does everyone see that? All right, so I guess I should label these. Well, no, that's probably fine. So now I do 2, 3, 4, 1, 5. And now j equals 4. And that means that k is the thing at 4, which is 1. And I is the thing before, which is 2. So it's the same setup as before. All right. So now while I is bigger than 0, well, I is 2. And AI is bigger than k. AI is 4, and that's certainly bigger than k, which is 1. So I'm going to have to do something. So what do I do? Oh, sorry, yeah. Yes, I is 3. It's pointing to the right thing. I just wrote down the wrong number. All right. So 3 is bigger than 0, and 4 is bigger than 1. So I do what's in my while loop. I set AI plus 1 to be equal to AI. So AI plus 1 is this, which is 4. And now I decrease I by 1, so it becomes 2. Is that okay? So really what's happening is I is now actually pointing over here. That's really what's going on. And now I look at my while loop, and it says, well, I is bigger than 0. Well, I is 2. And AI is bigger than k. 3 is bigger than 1. So I'm going to go inside the while loop and do whatever it says. AI plus 1 gets AI. So AI plus 1 is what? 4. And it gets AI, which is 3. So I put a 3 there. All right. And then the next thing I do is I decrease I by 1. So I goes from 2 to 1. So that has the effect of moving this arrow over 1 more to point to that. So now I go back to my while loop and I say, well, I is bigger than 0. Well, I is 1, so that's bigger than 0. And AI is bigger than k. AI is bigger than k. So 2 is bigger than 1. That's true. So I do whatever's in the while loop. AI plus 1 gets AI. So that means this 3 becomes what? 2. And the thing I do after that is reduce my I, so I becomes 0. All right, so now, while I is bigger than 0, well, I equals 0, so I'm finished with my while loop. So I go to the line after that, and that's AI plus 1 gets k. So AI plus 1, well, I is 0, so AI plus 1 is this right here. So that becomes k, which is 1. Right? And at that point, I'm done this iteration. So I have 1, 2, 3, 4, 5. So I'm done, but insertion sort doesn't know I'm done. The next iteration says, well, set k to be aj and I to j minus 1. So at this point, j equals 5, which means k equals 5. And I equals 4. Oh, I didn't do my arrow. I equals 4. And now we go into the for loop, or the while loop, sorry. While I is bigger than 0, so 4 is bigger than 0, and AI is bigger than k. So 4 is bigger than 5. That's false. So we skip the while loop, and we just set AI plus 1 to be k. Well, AI plus 1 is a5, and it's already equal to 5, so we don't need to do anything. So at this point, we're done, because the last iteration of the for loop is when it's 5, because that's the length of the list. And notice, once we're done, this thing really is sorted. So you can think about this in a slightly different way. Initially, we had 3, 2, 4, 1, 5. And essentially what we did was we swapped 2 and 3. That's really what we did. In this step, 2, 3, 4, 1, 5, we didn't need to do anything. In this step, we had 2, 3, 4, 1, 5. What we really did was we took 1 and stuck it at the beginning and bumped everything else down. That's really what happened. And then in the very last step, we didn't have to do anything. So the diagram on the right, that matches up with the diagram we had earlier. The diagram on the left is what the code actually does. Any questions about insertion sort? All right. So, well, again, we would ask ourselves, how long does this take? And I mean, there's nothing special about bubble sort. The answer is, it depends. I mean, it takes some amount of time. Okay, that's not necessarily that illuminating. One question that's natural to ask now that actually makes sense to ask is not how long it takes, but how long does it take compared to bubble sort? Because now we have 2 ways of sorting data. We have 2 ways of sorting numbers, bubble sort and insertion sort, and a natural question to ask is which one is better, where better in our case means takes less time. So how does it compare to bubble sort? And when you do that comparison, you assume same array, same hardware, same OS, all that stuff. Same operating system. So that makes a little bit more sense to ask, right? Because we don't need to worry about these differences between computers because now we're running the thing on the same computer. We don't want to know how long it takes. We just want to know which one is better, right? If one takes 30 seconds, the other takes a minute, we want to do the 30-second one for sure. All right. So this brings up the idea of analysis of algorithms. So what we try to do in this field is determine how long algorithms take to run. But we've already said that that's kind of hopeless. So really what we do is we come up with ways of comparing how long it takes algorithms to run. But before we can do any of that, we need to decide what takes time to do. So to determine how long an algorithm takes to run, we need to know how long the individual operations you do in that algorithm take. So an example of an individual operation would be something like how long does it take to add 2 numbers? One thing we used a lot in insertion sort and bubble sort was we compared numbers. So how long the algorithm takes depends strongly on how long it takes to compare 2 numbers. If it's very fast to compare 2 numbers, our algorithm will run quickly. If it takes a long time to compare 2 numbers, our algorithm will run very slowly. So examples of those operations would be addition or comparison, multiplication, all of those sort of basic building blocks. So how long the individual operations performed take. So to do this, what you do is you define a model of computation. That's what you have to do. All a model of computation is it says what operations you're allowed to do and how long they take. That's all it is. Question?
Oh, do we care at all about how much memory our algorithm takes?
Yeah, that's actually very important. It doesn't really get studied very much in the undergraduate curriculum. It does come up, and it is something to be mindful of for sure. Yeah, I like to point it out when we come across good examples of that, but that is an entire field of study. Yes, for sure. Other questions? All right. So there's many different models you could say, or you could use when you're analyzing your algorithms. So for now, let's say that comparisons, and by comparisons I mean less than or equal, greater than or equal and not equal, they take one time unit. And that's typically referred to as unit time. So it doesn't really matter how long it takes your CPU to compare two numbers. That's not really that important. What this is saying is, let's scale that to be 1 unit of time. And then I'll give my answer in these magical units of time, and then you can multiply through by whatever it is to make it work on your processor. It's actually more complicated than that, but that's the idea. So the actual amount of time varies, but we'll just assume it takes unit time, and it basically works out. The other thing is that in general, I mean, you could have equality is slower to check than an inequality, or vice versa. That's technically true, but it doesn't tend to make a large difference. So we assume not only that they all take unit time, we assume that they all take unit time. So they take the same time, and that time is 1 time unit. All right. So the number of such operations in whatever model you've defined is called the time complexity of the algorithm. The number of such operations is the time complexity of the algorithm. So you might say, I don't know, bubble sort takes 100 time units to sort a list. Right? That's probably not very illuminating because I didn't tell you how long the list was, but that's the kind of answer you'd get. You'd say it's the time complexity. It has time complexity 100. Typically, what we're interested in is the worst case time complexity of an algorithm. Right? So what's the absolute longest your algorithm could take on a list of length 100, say? Now for some algorithms, they'll run for the same amount of time regardless of what the list is. But other algorithms can take advantage of some facts to end early. So for example, bubble sort, as we talked about earlier, you can modify it so that if the list is already sorted, it finishes earlier. And in that case, the time complexity would sometimes be very low, but we're not really interested in that. We're interested in the worst it could be, right? Because if you want to set aside enough time for this to run no matter what, you should budget the maximum amount of time, not the minimum amount of time. Okay? So we're typically interested in the worst case time complexity. So what that means is the maximum number of operations performed. And we'll phrase that in terms of the length of the list. There's a question? Yeah?
The worst case for quicksort is the same as the worst case for bubble sort. Why do you consider quicksort a faster algorithm than the worst case?
Right, so a couple of things. The worst case for quicksort can be made to be better than the worst case for bubble sort. You can, if you're very careful about how you implement quicksort, you can make it go faster. The reason that we like quicksort is because on average it is better, and for some people that's good enough. So definitely you don't want to budget around the best case. Right? The best case is not a reasonable estimate for how long it will take. The average case can be. So most of the time it's okay. If you want to be guaranteed that all the time you'll be at most whatever, then you have to go to the worst case. Sometimes average is good enough. Other questions? Yeah?
For word sort, it actually says that it takes O of n log n. Right?
Yeah.
And then for quick sort, it's O of n squared, but O of n log n typically.
Yeah, so that's the average case.
So doesn't that mean that word sort is better because it's like it's worst case is O of n log n and not ever?
Yeah, so the problem is this big O notation that we'll see, it hides some constant factors. And what's more, the average case of quicksort is typically better than the worst case of merge sort. But it depends strongly on the data. So you can always find data that will skew that, usually. But it depends on your specific application. In the worst case, the official definition of quicksort, yes, it's n squared in the worst case and log n on average. But you can program it in a different way. If you're careful, you can make it worst case n log n. The problem is, in practice, it then takes longer, because on average it was doing well anyway. Other questions? All right, so let's think a little bit about these analysis things. So if we go back to our maximum finding thing I did at the beginning of tonight, what happens? So I gave that algorithm in English. I'll give it in pseudocode here, and the reason I'll give it in pseudocode is it becomes a little bit easier to analyze. So we have a sequence of n numbers, let's say in a list or an array. The way it works is this. Initially, max gets a 1, and then for I gets 2 to n. If ai is bigger than max, then max gets ai. And then at the very end you return max. This is exactly the algorithm I talked about at the beginning of the class, except this is in pseudocode, whereas at the beginning of the class I gave it in English. It's the same thing. All right, so how long does this algorithm take? So when you ask how long an algorithm takes, what you're really asking is how many operations do you have to perform, where an operation is defined in your model of computation. So in our model of computation, we're considering comparisons. So for now, let's say that comparisons take 1 unit time. So everything else is free. It costs nothing. The only thing that costs time is a comparison. If you wanted, you could define a model of computation where finding the max took unit time, and then this algorithm would take unit time. But that's not very interesting, right? Who cares? No one would actually use that model of computation anyway. It turns out that the model of computation, where you just count comparisons, that tends to be a pretty fair estimate for how long these things take. So this is a good model of computation. You can define it to be whatever you like. Just like if you went back to our stuff on logic, you could define the universe of discourse to be the empty set. And then you can say all sorts of crazy things, but who cares? All right, so how long does this thing take? Well, you count the number of comparisons you do. So the first thing you should do is figure out where the comparisons are. Where are the comparisons in this algorithm? Yep.
We're checking whether AI is greater than max.
Yes, so there's one comparison right there. Any other comparisons? Yeah? Yeah, in my for loop, I do comparisons. I have to. When I run through the for loop, I always check to see is I less than n? So I do one comparison here, basically, for lack of a better place to circle. All right, so that's where the comparisons are. So let's think about this a little bit. I use one comparison in each iteration of the for loop to ensure that I is less than or equal to n, and then one comparison inside the for loop to check if ai is bigger than max. So really the question becomes, how many iterations do I do? Yeah? So just the number of iterations for now. So n minus 1. And the answer is n minus 1 because the loop goes from 2 to n. And just like with summations, the number of times you go through it is the top thing minus the top thing minus the bottom thing plus 1. Right? Just like it was for summations. Top minus bottom plus 1. So this is n minus 2 plus 1, which is n minus 1. If you don't see that, think about, well, what would this be if the for loop went from 1 to n? Well, obviously there would be n iterations. This is going from 2 to n, so there should be one fewer, and that's why it's n minus 1. So we do n minus 1 iterations, and in each iteration, we do how many comparisons? Well, we do one in the for loop, and one comparison to check if ai is bigger than max. So that means we do 2 comparisons per iteration. So the total, you would think, would be 2 times n minus 1, but I would in fact argue that that is not quite correct. What am I forgetting? Yeah? Yeah, so the very last iteration that I would make is when I is n plus 1. But I don't actually make that iteration because n plus 1 is bigger than n. But whatever programming language I was in didn't just divine that answer. It had to check it somewhere. And the way it checked it was by checking to see how I compared to n, just like it always does. For n minus 1 iterations, that comparison will return true. That's why we do n minus 1 iterations. On the very last almost iteration, it will return false. So in fact, it's not 2n minus 1, it's 2n minus 1 plus 1. And this plus 1 is to exit the for loop. So the total number of comparisons is 2n minus 2 plus 1, which is 2n minus 1. That's the number of comparisons that finding the max takes using this algorithm. Okay, so a couple of things. Is this the worst case time complexity for this algorithm? Yeah, right? There's no way I can ever do any better than that. Right? I always have to look at every single element. There's no shortcut like there was with the modified bubble sort we talked about. Right? There's no return somewhere in this for loop. It's always going to go through the for loop the exact same number of times. And in fact, you know, you sort of have to, right? If you're finding the max, you can't help but look at every element. Because if you don't look at one of the elements, well, what if the max is there and you missed it? Yeah?
Does it not take time to set variables?
Yeah, absolutely. But the only thing we're counting is the number of comparisons. So comparisons are the only thing that take time. Now that might seem strange, and it is, but as we'll see later, counting those other issues doesn't really affect the behavior of how long this thing takes. So yeah, maybe it takes some amount of time to set those variables, but that time pales in comparison to the comparisons. Other questions? All right, so one other issue about this is you can ask yourself, what's the sort of behavior of this function? What's the behavior of this function? What does this function look like? So 2n minus 1 is a line. If you view it as a function of n and graph it, it will look like a line. So that means this function, or this algorithm, takes time that's linear. And that's important when you think about the behavior of what happens with this thing when you start to add more and more and more and more elements to your list. So as the number of elements increases, the number of comparisons it takes to find the max will also increase. But it increases in a linear fashion. And that's something that's really, really important. Because it could be something else, right? For some problems, maybe as you increase the number of elements, the amount of comparisons grows exponentially. That would be bad. Maybe it grows quadratically. That would be not so great, but probably not the end of the world. Here it just grows linearly. And that seems like it's pretty reasonable, right? As I increase the number of elements, I increase the amount of work, and there's a linear relationship between those two things. That's pretty reasonable. So what we're going to do next time is analyze bubble sort and insertion sort so that we can compare those. And then we'll get away from this level of precision, because as we'll see, the only important thing is that this function is a line. So that's it for tonight, and enjoy your break.